All right. Okay. So let's get started. The first part, yeah, the ideal op-amp assumption. So the ideal op-amp assumption, I wish I had my iPad. We have this thing in, I can maybe write it in chapter 3, first or second page. It's literally written down there. Probably, if you see the lecture note, probably somewhere down here. It's what's the ideal op-amp assumption we have. So the input impedance of an ideal op-amp. So if we assume this is an ideal op-amp, the input impedance has to be very large, like infinity. That's our assumption here. And the current that is flowing into the op-amp, the current that is flowing in here or there to the input nodes, that's going to be 0. That's our assumption. Very, very small current is flowing in or out. In other words, you can think the impedance here, there's a resistor in between these two input nodes, and this guy has a very large impedance. What does that mean electrically? It means this bridge is basically broken. So you can't have any current flow in or out or cross. Okay, so that's the reason why we assume the current is going to be 0. And if there is a negative feedback loop, like what we have here, negative feedback loop means this. Your output is being fed into the negative node. So if we had that, the relationship between the voltages at these two input nodes, here and there, the relationship is they are going to be the same. And for this situation, we just happen to have V positive equal to 0. So this was just 0. So, but this is like a redundant information. This is the actual answer. Even if you just put it like that, or if you wrote like 0, I still made that as a correct answer there. Okay? But this is not the actual answer. This is the actual answer. Okay? All right. Any questions up to here? I hope this is going to be helpful from now on. And let's move on to the next part. So from the circuit in this figure number 1, we have RS is 2K and RF is 25K. So we have, this is 2 kilo ohm and this is 25 kilo ohm. Okay? And the op-amp in this figure here is an inverting amplifier. Inverting amplifier, because my signal is going in to the negative node. Okay, so we have this feedback, and this guy is going into the, what was that? Into the negative node. Okay, so it's a inverting amplifier. And the gain of this ideal circuit, okay, that one is what? The gain is minus RF over RS for an inverting amplifier. So we have 25K over 2K, and K is basically 1,000, right? So K and K go away, so it's 25 over 2, so it's going to be minus 12.5, or if even though you just write 12.5, that's all fine. Okay? And what's the main meaning of this gain? That's V out over V in, right? And actually it's the magnitude ratio. Okay, so V out over V in ratio is 12.5. That's what we have. And the next problem here is looking for the amplitude of the output voltage if we had an input that was a sine wave having 1 volt peak to peak. So we have 1 volt peak to peak signal. Peak to peak is 1 volt. and that is going in. And what we have is 12.5 times greater gain. And my output, we expect, is going to be like this. Oopsie. Is going to be like this. And this we have 12.5 peak to peak, right? Because it is bumped up 12.5 times up, right? And the question was looking for the amplitude. So in that case, the amplitude is going to be half of this, so 6.25. So 6.25 was the answer for this. All right? Okay. And the next problem here was about this one here. When the supply voltage was 10 volt, plus or minus 10, sketch both the input and output waveforms for a sine wave input with a frequency of 100 hertz. And I want you guys to consider the practical limits. All right, and they show all the details like the peak value and the cycle time. So 10 volt. So I saw some students made a mistake caught by this 10 volt. This 10 volt is a supply voltage. It's like, oopsie. We have an op-amp like this, and we have signals going in, and this is going to be my out, and this is going to be my in. And we are providing plus and minus like that as well. So these are, we talked about this terrible analogy. If you remember, we have this coming from the wall, and we have this 110 volt coming from the wall. So this is the internet, Wi-Fi or whatever, and we have 110 volt to the TV. And this is the signal, so you can watch Netflix. And this thing is just power to turn the TV on, right? Same thing. This guy is just the power to turn this op-amp on, supply voltages. So this was 10 volt and this was minus 10 volt. And these were the input signal. You have a triangular, you have a triangular wave going in, you have a sine wave going in, you have a square wave going in. Those are the signal, and then the output, you have a very large sine wave, like square wave coming out, or you have a sine wave coming out, whatever. Okay, so these are the input and output signals, and this supply voltage is the 110 volt we use to turn the TV on. Okay, so don't get confused about that. Okay, anyway, so the configuration we have is we have this 10 and minus 10 volt being supplied, and here we're providing a sine wave that is 2 volt peak to peak. So from peak to peak, this is 2 volt, and I'm looking for the output, right? And what was the relationship between the input and output in our case? It was 12.5 times getting larger, and we had to flip that thing, right? So if we draw this thing, this was time, and let's say this was voltage, we had a sine wave like that. And this is 1 volt, this is minus 1 volt. That way we have 2 volt peak to peak. Okay? And our output is going to be flipped, and it's going to be 12.5 times larger. So we're going to have something like this. And this one here is going to be 12.5, and this one down here is going to be minus 12.5. Okay? If it were an ideal situation, we would have something like this. However, we only provided plus and minus 10, right? So the output we obtain is going to be between plus and minus 10. We can't have an output that is greater than 10 or smaller than minus 10. That's like it's like fair, right? You only provide like 10 and you're expecting like 200. And you can't have that. The max is going to be 10 in this case. So it's going to go down, and then it's going to be capped at this point. It's going to go up, and then it's going to be capped. It's going to go down, and then it's going to be capped. It's going to go up, capped, go down, and capped like this. So that's what we expect to see. Okay? And this is one of the things that we're going to be doing in the lab this week, or some of you guys already did in the other labs. All right? Okay. Any questions up to this point? Okay, if not, let's move on. And then the next one here, I was actually going to ask you guys about what's this circuit, but I was a little bit afraid some of you might answer wrong, so I gave you this. It's a practical integrator circuit, which means maybe I can ask you guys in the exam later. I don't know. But this is a practical, again, integrator circuit, and integrator circuit is can be identified by this capacitor in the feedback loop. Okay, and in order to make it as an integrator, a practical integrator, we're adding this additional resistor there, right? So it's an integrator circuit, and RS we have is 1K, RF we have is 20K, and the CF, this value is 0.1 microfarad. And what's the cutoff frequency? In hertz. So cutoff frequency, omega cutoff, is 1 over RF CF. If you remember, I told you guys the cutoff have same subscripts. So 0 decibel is going to be 1 over RSCF. And that's this is in radian per second. And in order to convert this thing into hertz, you need to have 1 over 2 pi, right? RFCF. And we can plug in the numbers in here. So once you are up to this point, most of you did well, but let's just try. So it's 1 over 2 pi. Its RF is 20K, so 20 10 to the third. And we have CF is 0.1. Micro is 10 to the negative 6, right? So if you do the math, you may get something. I'm not really sure. I think it was like 80 hertz, something like that. Don't trust the number here. But I believe it was around like there. And this is going to be around like 1600 hertz or something like that. Okay? So that's how we obtain these values. And then the next problem was about sketching the frequency response to Bode plot of the above circuit and indicate the cutoff and 0 decibel frequency and axis labels on your sketch. So this is going to be in the frequency in log scale, and this is going to be V out over V in magnitude in decibel unit. All right? And the graph may look like this. And it starts to roll off or cut off. Where's back? It's cut off is here, and you have your F0 over there. Right? And basically that's it. So that's the Bode plot of this practical integrator circuit. And then the next problem was about if the input frequency was lower than the cutoff, will the input voltage be integrated ideally or not? Why or why not? And if my input frequency was in this range, lower than the cutoff, then it's not going to be integrated ideally. If you remember, the ideal integrated circuits, the Bode plot of the ideal integrator circuit was looking like that. And here we had an issue, right? The output over input ratio is becoming very large. It's going up to infinity. In other words, you're providing only like 2 volt, but you're getting like infinity voltages. And I told you that's usually wrong or not desirable, because if you have a very large value coming out, it's like exploding, and you don't want to have that, or not possible. So they came up with this idea to cut it off, right? So if this Bode plot follows a straight line like that, then it is matching with the ideal case. So it will be, your input will be ideally integrated. But if you have your frequency in this range, your practical response is way different from the ideal case. It's way different, right? So it's not going to be integrated. So the answer is no, and you can explain that thing as I wrote down here, or you can just say it works as an inverting amp in that range. That's what I wrote in the lecture notes. Okay? And then the next question is, these two are basically same ones. So it's looking for the desirable frequency band. And the desirable frequency band is this range, right? We want to have this thing in, what's that? We want to have it, it's here. We want to have it in this range, so that your practical response is same as the ideal case. You know, in other words, it's being integrated correctly. On the other hand, we do not want to go in this frequency range. Anybody remember why we're not going down in this range? Anyone? What was that?
You won't see the output.
Yeah, we will not see the output. Look at this. The vertical axis here is output over input ratio. So let's say we fixed our input as 2 volts, and we are changing the input frequency and see what my output voltage is going to be like. And my output voltage amplitude is going to be pretty large, and then it's getting smaller and smaller and smaller and smaller and smaller as I increase the frequency up and up and up. And this is actually what you're going to do in the lab as well, or you must have done already in the lab. As you increase the frequency, you keep it in the low frequency like that, and then you measure the amplitude, or you keep it a little bit high frequency fluctuating faster, or you keep it fluctuating really fast like that, and then check what the output amplitude is going to be like, and then you find that ratio. And if it is above this frequency, or if your input moves too fast, faster than this rate, then your output is going to be smaller than your input. That's this 0 decibel frequency, right? So we don't want to use this range. We want to use this range. And if you remember, I also told you guys, if you have that luxury of choosing the range, you may want to go up this range where, see, around like here, it's kind of following, the red line is following the blue line, but still we have a little bit of gap here, right? But in this range, they are almost identical. So you may go a little bit higher, like for example, 10 times of your cutoff frequency and lower than your 0 decibel. That's what you want to have. So in our case, my FC was 80 hertz, my F naught was 1600 hertz. So you can do 0.0 kilohertz to 1.6 kilohertz. That's the range, or you can try 0.8 kilohertz to 1.6 kilohertz. Something like that, if you want to make it a little bit more tight. Something like this. This is 80 and this is 1600. Okay? This part, many students did well, but any questions? Yes?
Like, if there was something like this, let's say like you had a like differentiator one, and just like whenever like you said what's the desirable frequency, it's not going to be a certain number, it's just going to be like a range in between our numbers that we.
Yes, it may be a range, or I will specifically ask for what's the frequency band, or what's the value, or something like that. So it may depend.
So if you ask for a specific value, we can still give a range, or you solve for a specific value?
If I'm asking for a specific value, I'm looking for a specific value.
And then also I had a question. You scroll up with part A.
Okay.
So when you said like, you know, like this is a practical integrator, what would make it a practical differentiator?
Oh, okay, a good question. So we have a circuit like this, and we have VN going in like that. This is an inverting amplifier, right? And every time the story starts from here. From here, if you replace this with a capacitor, then it becomes a integrator. And if I go back, if I keep it as a resistor but replace this guy with a capacitor, it becomes a differentiator. And if I add another resistor here, yes, it becomes a practical differentiator. Okay? All right, very good question. Yes?
So when you say practical, it's basically just adding a resistor?
Yes, it's not, but you need to add the resistor at the right place, and with the right value.
You got your capacitor inside that one. The differentiator is on the outside.
Yes, yes. Okay? Okay, all right. Okay, and let's try this last one. So this part, many of you unfortunately didn't do well, so I hope this is going to be helpful. And this one is, so in chapter 4, in the very first page, bottom side of the very first page, like around like here, we had this example problem. I did a little bit of math to show you that. And if you also go to that example problems posted on Folio, one of them for chapter 4, if you open it up, you will see almost exactly same thing over there. Okay, so if you want to go back to the math, you can check from over there. But let's try this thing here. So sketch both the input and output voltage waveforms for a square wave that had 1 volt peak-to-peak input with a frequency of 1 kilohertz. and show all the peak, detailed peak value cycle time. And so let's say this is T, this is voltage, and we have something like this as a square wave, and peak to peak is 1 volt, right? So this means it's 0.5 here, and then this is minus 0.5. Okay, right? And this is my input. So we have the input waveform, and we have the peak values, and then, what's the cycle time? Cycle time is the period, basically. And it's said we have a 1 kilohertz signal. So it means it has 1,000 cycles in 1 second. That's the meaning of hertz, isn't it? So we have this up and down. We have this 1,000 times. We have these 1,000 times. 1, 2, 3, up to 1,000 times in 1 second. So this one cycle is going to be 1 over 1,000, right? So the time here is going to be 1 over 1,000 second. Okay? And then we need to think about the output. So the output is, Vout is, it's the integrator, right? So I think it was minus R. Where's the eraser? Something like this. And we have our SCF. That's what we have. We need to solve this one. And we tried this thing in class where, oopsie, well, this is step number 1. This is another step. So we are integrating, we're flipping it over, we're multiplying this value. That's what we tried. So if we just consider this time range, my input is just a straight line. It's a constant, right? So if we integrate a constant, it becomes a ramp, isn't it? So it's a positive constant, so it's going to be a positive ramp. But I need to flip it over, so it's going to be a negative ramp. And I need to multiply this value, so it may be a little bit flat, or it may be a little bit steeper. Right? So let me just draw that thing down here. We may have something like this. And then this part is actually going up like that, because you can easily think the value here and the value there are basically the same. These are both 0.5, so this one, that one, they are the opposite. And it's going down like this and going up like that. So it's going to do this forever. Okay, so that's the waveform of our output. Okay, you have a question? No.
Me?
Yeah, no. Yeah.
So do you not, so yeah, you integrate it, you flip it, you multiply it.
Mm-hmm.
So do you not do that for every single component? Because I think that's where I went wrong on this problem. So at first I had the triangle like that, but then I was like, those two like middle ones, it's like you get that first line and then where it makes that triangle.
This one here?
Part. Yeah, so if you go like over, that bottom one.
This one here?
Yeah.
Yeah.
So I was like, okay, well, that's what that should look like. It's negative, but then flip that to make.
Yeah. So yes, this is, let's say this is minus 0.5, right? So what we're doing is minus 0.5 dt. right? So if we do this, it's going to be minus 0.5 t, right? Just math. It's pure math I'm talking about. So minus 0.5 t is this. If this is time versus whatever, y, then it's this graph, isn't it? This is minus 0.5 t, right? And from there, we need to flip it over. So this is going to be positive 0.5. So it's going to be like that. So we're having a graph looking like this. Okay? And again, all the rigorous math is provided in that lecture note that we did, and also in the example problem, the lecture note for the first page or the second page, and in one of the PDFs that I posted for the additional example problem. So yes, okay. And the last part is we need to find the amplitude here. Yes.
Why wouldn't it pass the center line?
This and that has to be exactly the same or symmetric, I would say, because it's based on the same values. This is 0.5, this is minus 0.5, and so on.
I think I'm wondering why it doesn't look like that instead. Like jumping at the same points.
No, or so that's a good point. To make it more rigorous, this equation actually has to be of t is v out of t1 let me write this thing here. V out of time t is going to be v out of time 1 minus 1 over RSCF integral time 1 to time 2 of Vn dt. Okay, and here we just naturally assume especially for the very first point, we just assume it as 0. But when you integrate for this time period, if you consider this as t1 and this as t2, you're starting from this point, which is here. So why do we have a circle there? It is starting from here. So from this point as an initial value, and from here it is growing. And at this point, when you're integrating this time period, which is for this guy, this point here becomes t1, and this becomes t2, and this becomes your initial value, and from there it is going down. Does that make sense? This is just pure math. Okay? All right. So back to that pure math part, I wanted to find out what's the value of this point. So we'll literally have to do a little bit of math here. And for this case, it's 0.5. So it's going to be from 0 up to, so this is going to be my T1, and this is going to be my T2. My T1 is 0. My T2 is half of this period, right? So my T2 is going to be 1 over 2000. And my Vn is going to be 0.5 dt, right? And it has to be minus Rs is 1K, and CF is 0.1 micro. So it's going to be 0.1 micro is 10 to the negative 6. So if you solve this, we're going to have a value at this point. Okay, so if my memory was correct, we have something like minus 2.5 or something like that. Alrighty? Okay. Any questions about this point? Yes.
What would cause it to start positive and go down?
What was that? What would
cause it to start positive and go straight down to the negative and jump across that center line axis?
What would make it like this?
Yes.
If you had the initial value starting from here, then what's this? If we had the initial value starting from here, then it will go down to this point, it will go up to this point, it will go down to this point, it will go up to that point.
But what would cause that initial value is what I'm asking.
This initial value, we just assume this to be 0. Yeah.
No, I'm saying what would cause the initial value that is above 0? Like, what part of the function would cause that?
That's something has to be assumed. Okay, does that make sense? It has to be assumed. The initial value, usually it has to be assumed.
So could we assume it as anywhere we would like it then?
Yeah. Here, it was not provided. Let me see. It was not provided. It was just following what we had in the lecture note. But if and so here, I just assumed it was starting from 0. But if you assumed it is starting from 10, then you can have it from 10, and then start this math. If you assume this as we had -10, then from -10, we have this waveform, something like that. Okay? All right. Very good point. Okay. Any other questions? All right. If not...